Hello and welcome to today's webinar. We would like to first start by reminding everyone that abstracts for Pacific PNT 2026 are due in 2 weeks on Wednesday, November 5th. Today's webinar is titled Robust Interference Mitigation in GNSS Snapshot Receivers, based on a paper published in the summer 2025 issue of Navigation, the Journal of the Institute of Navigation. This paper can be viewed on our open access website at navi.ion.org, where you can read, download, cite, and share this technical paper and many others. Today's webinar is being presented by Elena Calatrava, one of the paper's authors. Elena received her BS and MS degrees in electrical engineering from UPC in Barcelona, Spain in 2020 and 2022, respectively. She is currently a PhD candidate in electrical and computer engineering at Northeastern University's Information Processing Laboratory in Boston, Massachusetts. Her research focuses on statistical signal processing, robust estimation, and multi-target tracking algorithms to improve resilience in satellite-based navigation and radar-based localization systems, with an emphasis on cooperative and distributed architectures. She was a co-recipient of the Best Track Paper Award at IEEE ION Plans 2023 for her work on federated learning for GNSS jamming signal classification. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions using the Q&A button in your viewer. Thank you everyone for joining us, and we will now turn the time over to Elena.
Thank you, Beth, for the introduction. Hello, everyone, and thank you very much for joining today. In this presentation, I will be talking about our recently published paper in the Navigation Journal titled Robust Interference Mitigation in GNSS Snapshot Receivers. This work is a collaboration with Adrià Gusí Amigó from Alvora Technologies, Fleur Melman from the European Space Agency, and of course, my advisor, Professor Paul Closes, here at Northeastern University. I want to say that it's a real pleasure to give this presentation as part of the Institute of Navigation's webinar series, and that I'm truly thankful for the opportunity to promote our work today. So before starting, let me give you a quick overview of today's presentation. So I will begin with the introduction of the motivation for using robust signal processing methods to protect GNSS snapshot receivers and the main challenges involved in this task. Then I will describe our proposed approach, the Snapshot Robust Interference Mitigation Framework, followed by the main results and experiments, and I will conclude the presentation with some remarks. I would also like to highlight that this work is an extension of our conference paper presented at ION GNSS Plus in 2023, 2 years ago. So to start with, GNSS jamming, which can be intentional or unintentional, refers to the emission of radio frequency energy within GNSS bands that consequently interferes with the receiver's operation. We should recall that GNSS signals reach the receiver with extremely low power because they come from satellites that orbit about 20,000 kilometers from the Earth. And in contrast, most jammers operate on the Earth's surface, and consequently their signals arrive much stronger and completely overpower the received satellite signal, which is very weak compared to the jamming signal. As a result, the GNSS receiver's performance can be severely degraded or even lost entirely in the presence of jamming. And in fact, it is important to note that even a single jammer can disrupt receivers across several square kilometers, making this a major concern and an active area of research in our community, in the Institute of Navigation community. So let me highlight that jamming is becoming every day a more critical large-scale global threat to GNSS-dependent infrastructure, and this is, of course, of our concern. As reported in this GPS World article from 2024 that we are citing in this slide, analysis of CubeSat and aircraft data show that GPS jamming has reached unprecedented levels, disrupting aviation, spaceborne sensing, and navigation systems across Europe and the Middle East. Beyond large-scale events, we are also seeing a growing number of jamming sources on the ground and in everyday civil applications. Um, we all know that cheap portable jammers are widely available online, which makes it very easy for basically anyone to interfere with GNSS receivers, sometimes even just to protect privacy, just for privacy concerns. And finally, as I mentioned before, and very interestingly, jamming effects can also arise from non-malicious emissions. For instance, from legitimate aviation aiding systems like DME and TACAN, for which we have pictures here, also from damaged electronics or from harmonics of wireless devices that leak energy into the GNSS bands, although they don't transmit into the GNSS bands themselves. And this is what we know as spectrum crowding, which is also a concern of ours. So now that we've seen why jamming is such a widespread problem, in this slide, I aim to explain why the pre-correlation stage of a GNSS receiver is the most effective place to apply anti-jamming in the presence of strong interferences. So during correlation, as we all know, the receiver integrates the signal samples over time, and this spreads the interference energy across the correlation output domain, which is across the delay Doppler space that you can see in here in these cross ambiguity function plots. So here we see on the right a clean cross ambiguity function plot, and on the left, one that is obtained from a jammed GNSS signal. And as you can see and very easily understand, the interference completely distorts the correlation surface, making it very difficult to separate it from the actual useful GNSS signal. So basically, the key takeaway right now is that the best opportunity to suppress strong jamming interference is before correlation, when we can still act on the raw samples and where the interference basically remains localized and observable. Widely used pre-correlation methods include the adaptive noise filtering, which relies on certain assumptions about the jamming signal waveform and often requires parameter tuning, and also the widely spread and popular multi-antenna solutions like CRPA are used widely, but they tend to be heavy and costly, as one can understand, because they require the use of multiple antenna elements. Considering all of this, we have a very clear motivation to use signal processing-based methods that are waveform agnostic and single antenna compatible. And in this work, we focus on the robust interference mitigation, or RIM framework, which was originally proposed by Daniele Borio, my advisor Pau Closes, and Hao-Ching Li. So our study is motivated by the growing trend of cloud-based GNSS processing, which allows computationally intensive tasks to be handled remotely, which is of course of our interest. And in order to enable this, we resorted in this work to the use of snapshot architectures. With snapshot architectures, only short chunks of raw samples are captured locally, and then they are offloaded to the cloud for processing. And as we are all aware of, this approach allows for low power and low cost operation. And this is because the receiver basically can stay idle between snapshot transmission and only transmit these small data bursts at each time. To further save bandwidth and power, these samples are often low bit quantized, which simplifies transmission, which is beneficial, but also it reduces the available information about the jamming waveform. And as a result, maintaining robust interference mitigation in this context becomes challenging. And this is precisely what we study in this work, how the RIM framework performs under snapshot low bit conditions. Now I will introduce the RIM framework and how we adapted it for snapshot architectures. So we start from the signal model, of course. Here we have the IQ baseband snapshot samples at the output of a GNSS front end. In this expression, we can see the useful GNSS signal, the thermal noise, eta of n, and also the jamming component, which we denote as I of n. The idea behind robust signal processing methods is that any received sample that does not follow the assumed nominal model, which is additive white Gaussian, is considered to be an outlier. And by identifying these outliers, the robust methods are able to downweight their influence during processing, and as a consequence, reduce the impact of interference in the subsequent GNSS baseband processing. Here in this slide, we also define the jammer to noise ratio metric, which we will use later in the experiments to quantify interference strength. And I would like to highlight that this metric is proportional to the jamming signal amplitude, and therefore it quantifies its strength. So before diving into how the RIM framework works, I would like to briefly introduce the concept of a sparse domain, which is key to understanding the operation of RIM. So on the left in this slide, we see a spectrogram with clean GPS L1 signal, whose energy is, of course, as expected, spread uniformly across the frequency axis. And then what happens is that once we add a continuous wave jammer, as you can see in the spectrogram in the middle, or a chirp jammer, on the spectrogram on the right, is that most of the signal energy, which comes from this jamming signal, becomes concentrated in just a few frequency bins. So that means that in this transform domain, in this case frequency, the jammer becomes sparse, which means that it occupies only a small subset of coefficients, and that the useful GNSS signal remains broadly distributed. Basically, the punchline of this slide is that this property of having interference energy focused in a few locations is exactly what robust and sparse domain methods exploit for effective mitigation of the jamming signal. So some slides in the presentation will have a blue background, which means that the content, the material found here cannot be found in the paper. Instead, it comes from part of the response letters that we sent to the reviewers through the reviewing process in the navigation journal. So here I would just like to highlight a bit the intuition behind the behavior of a chirp interference in the frequency domain. So basically, a chirp is an interference that attacks a tone that is varying with time. So the interference first starts attacking an interference F1, and then it sweeps until attacking an interference F2. So it's like a continuous wave signal that is changing with time. So then thing is, if we plot the continuous time Fourier transform expression that we see here in black of a chirp interference, we see that instead of having one tone, as we would have with a single tone continuous wave, the bandwidth of this interference is spread over the frequency. And one may ask, if we have this huge or wider bandwidth being attacked, why are we able to represent this interference in a sparse way in frequency? No? And the answer to this is that this is possible thanks to the periodicity of the chirp jamming signal. This can be understood from these little equations that we have here, because a periodic chirp signal can be expressed as the convolution of a one-period chirp by an impulse train. Convoluted by an impulse train, and this results in the frequency expression of the CTFT that we are seeing here in black of the chirp signal for one period multiplied by the Fourier transform of the impulse train, which is again an impulse train with a scalar coefficient multiplied. So this means that the behavior of a chirp in the frequency domain is the original behavior multiplied by this impulse train, and consequently we can see these delta functions in the frequency, which, as you can see, show this sparse behavior, and they are equally spaced inversely proportional to the actual period of the chirp interference. Now that we've seen how jammers become sparse in certain frequency domains, I want to start looking at how the RIM framework works and how it uses this sparsity property. So RIM works basically with three main processing steps. First, the received signal is projected into a transform domain where the interference admits this sparse representation. Second, the outlier components are downweighted through a robust nonlinearity, which reduces the influence of the outliers without the need to know the exact jammer waveform. This is why we say that the RIM framework is waveform agnostic. The third and final step corresponds to when the clean signal is brought back to the original domain using a last linear transformation, which is simple. It is simply the inverse of the first transformation. So we have here that the composition of T2 with T1 is the identity. And finally, it is very clear that the output of RIM is a cleaned version of the original output front-end signal, which we can then feed into the cross-ambiguity function, or CAF. So someone may be wondering why we are applying the nonlinearity directly to the transform samples instead of applying it later in the estimation stage. And basically, the reason is that under the weak signal assumption considered in GNSS, it can be shown that applying an M estimator to jointly estimate delay and Doppler leads to the same optimization problem as computing the CAF with the samples that have already been processed by the nonlinearity. This is explained with a lot of detail in the myriad nonlinearity for GNSS robust signal processing paper by Daniele Borio. If anyone is interested in this, please check this paper out. And here, basically, in this slide, we look at the nonlinearity used in RIM, which corresponds to the derivative of the Huber's laws function. Here we have the derivative psi h. So the Huber laws works by weighting samples quadratically when they follow the assumed nominal model, which corresponds to a Gaussian regime, and linearly when they deviate strongly from the assumed nominal model, which would correspond to this Laplace regime that we see here in this lecture. And this behavior allows to have an estimator that acts like a least squares for nominal data while smoothly reducing the impact of the outliers in the data. Theoretically, this threshold TH has this expression here, and as you can see, it depends on the signal variance, which of course we need to estimate in a robust manner, because as we are mentioning, we are under the presence of a jammer. So in order to robustly estimate the variance of the signal, we resort to the median absolute deviation measure of statistical dispersion. In these slides that follow, I will discuss the adaptation of RIM to snapshot receivers. So unlike conventional GNSS receivers, snapshot architectures do not use a tracking loop, and instead data is processed in batches and not continuously, as I explained in the introduction briefly. However, I would like to mention that this is definitely not a limitation in adapting RIM to snapshot, because RIM in conventional receivers already operated in 1 millisecond batches, matching the GPS integration time. In our case, what we do is to leverage the fact that our snapshots were much longer than this integration time. They were of about hundreds of milliseconds. And what we do is to improve robustness by estimating the signal variance recursively across the smaller integration time segments. I believe this is clearer with the diagram in this slide here. So here we see the full diagram of snapshot RIM. The snapshot is divided into m smaller batches, each containing n m samples. And for every batch, we compute its FFT to bring the interference again to the sparse domain. These FFTs can be done in parallel. And then, of course, for each batch, we compute the median absolute deviation, and then we can improve the robustness by doing a recursive update of this value. But anyway, to recap this part, I would repeat that the lack of the lack of tracking loop is not a challenge in applying RIM to snapshot architectures. However, the real challenge from this comes from the low bit quantization that is desired with these low power devices. As I mentioned before, the low bit quantization is used to reduce bandwidth and power and to reduce the transmission costs. But of course, this limits how well we can characterize the jamming framework. Recall that anti-jamming methods are typically assessed assuming high resolution of the signal, of the jamming signal, and that therefore this motivates great part of our study, which is to assess how the RIM framework can be adapted to operate in a snapshot architecture and what the impact of this low bit quantization is. Because as I'm mentioning, most studies in the literature assume the capability of fully representing the jamming signal component. So in the following slides, I'm gonna present the results for the first experiment, which was run with simulated data. First of all, let me briefly summarize the system setup for this simulated data experiment. We considered GPS L1, Galileo, L1, and Beidou B1 signals, all with carrier-to-noise ratio of 45 dBHz. Each snapshot had a duration of 120 milliseconds, and the sampling frequency was set to 4.5 megahertz, which corresponded also to the receiver bandwidth. Regarding the quantization setup, we tested different numbers of quantization bits in order to analyze how this signal resolution changed the ring performance, and we evaluated results for 2, 4, and 8 bits in most of our experiments. And also, yes, I would like to highlight here as well that the quantization thresholds can be defined according to the expression here, and that the signal, in order to be quantized, must be scaled by an optimal automatic gain control factor that basically keeps the dynamic range of the signal proportional to its variance. All this content in the paper and in this presentation, of course, regarding the quantization of the signal comes from Daniele Borio's PhD thesis, particularly from his chapter 6, which I highly recommend if anyone is interested in the quantization of GNSS signal. So we simulated in the experiments 3 types of interference. The first one was a continuous wave jammer, which appears as a single narrow tone, as we can see in this first spectrogram. Then the second assessed interference was a chirp jammer, like the one we already introduced in the previous blue slides from the response letter when we explained the intuition behind the behavior and frequency of these interference. And finally, this jammer 3 is an interesting interference because it's also a chirp, but it has a pulsed effect in time, basically because the interference, the frequencies that are being swept by these interference cover also frequencies outside the receiver bandwidth. And this means that the interference is observed as having an intermittent behavior because under some time instance, the attacked frequencies are outside the receiver bandwidth. As you can imagine, the idea behind trying this interference was to also test the performance of RIM in the presence of a jammer that was not only sparse in frequency, but also in time. And we will actually see in the results how the continuous wave jammer, which has its energy focused on one tone, was a bit more challenging to mitigate for RIM than the chirp and its subsequent mode of post-time chirp jammer, because they have the interference more spread across the bandwidth of the receiver, as I shown before with the power spectral density of the chirp. Here we show some results of the impact of signal quantization, still not applying RIM, but we just want to see how quantizing the signal with low bits affects in how we characterize the jamming signal from the receiver perspective. So in these plots here, we have the power spectral density and the spectrogram of a single tone jammer for 8 bits on the left and 2 bits in the right. With 8-bit quantization, we have enough resolution to fully represent the jammer, and we clearly see the narrow single tone as expected. However, and interestingly, when we reduce to 2 bits, waveform distortion is introduced, and the low-bit quantization creates this additional frequency harmonics, which can show how the jammer power is becoming more spread across multiple frequencies instead of being focused on the original tone. This spreading of jammer power that I just introduced across multiple frequencies has the effect that the receiver is not able to fully observe the huge power difference between the GNSS signal and the jammer when, again, it operates with low-bit quantization. We can see this effect also in the plot on the left, where we see the results for effective jammer-to-noise ratio as a function of the actual jammer-to-noise ratio used to generate the interference. When the signal is quantized with only 2 bits, which is the result in green, we see that the effective jammer to noise ratio quickly saturates around 5 dBs, even though the actual jammer to noise ratio reaches up to 40 and 50 dBs. Another consequence of this limited dynamic range with 2-bit quantization is reflected in this table on the right. Here we show the median absolute deviation values obtained for different quantization levels and in the presence of the 3 studied interferences. And basically, we can observe that for 2 bits and for jammer 3, which was the one that was also sparse in the time domain, not only in the frequency domain, the obtained median absolute deviation values still closely capture the true signal statistics. I am highlighting this in this slide because it's important to understand that with snapshot RIM, accurate variance estimation with a median absolute deviation enables better thresholding in the Hoover zero minor linearity. And this in turn results in a stronger RIM performance because we are thresholding the data more accurately. In this figure here, we show the number of detected satellite vehicles as a function of the jammer to noise ratio in the presence of the first jammer, of the single tone continuous wave jammer. And we evaluate this for 2, 4, and 8-bit quantization, both with RIM disabled and with RIM enabled. So here we see that when RIM is disabled and for 2-bit quantization, there is some kind of robustness thanks to this limited awareness from the receiver about the GNSS jammer power imbalance. But however, as expected, RIM provides performance gains that are proportional to the resolution used to represent the jamming signal. So the higher the quantization bits, the better performance of RIM, and we observe higher gains, which is what we would expect. In this figure, we observe the results for 3 different metrics. So again, we have the number of detected satellite vehicles, the PVT availability, and the average carrier to noise ratio as a function of the jammer to noise ratio in the simulated signal. So there are some takeaways from this slide here. The first one, of course, is that when we don't use RIM, the gains are very low. Like the receiver shows how its performance is completely jeopardized because we are testing very high and powerful jammer to noise ratios. But however, as I was mentioning before, once we introduce RIM and given that now we have enough characterization of the jamming signal, we obtain considerable performance gains, even for the single tone continuous wave jammer, which was very challenging. With this slide, I wanted to show this 24-hour specification test that we run in order to show that the overhead introduced by RIM was only of 0.31 seconds or 2% in time to first fix for the configuration that we used, and that overall the cost that we observed in terms of this metric was negligible compared to the added anti-jamming protection. So this kind of confirmed the real-world feasibility of the method. And finally, I will just briefly mention that in the response letter, we also included some results from a comparative experiment between RIM and the notch filter for different bits of quantization. And we observed that the gains of RIM were better than the gains obtained with the notch filter for all the quantization bits tested. So now we move on to the last experiment, experiment 2, where we basically tested the snapshot RIM under more realistic conditions. And in this part, we used realistic GNSS recordings in the presence of hostile threats provided by the European Space Agency's team, particularly by Flor Melman, who we were collaborating with. In this second experiment, our goal was to benchmark the snapshot RIM framework against a commercial off-the-shelf receiver under realistic jammed conditions in this controlled environment. The tests were conducted using ESA's radio frequency constellation simulator, which generated realistic GPS L1 and Galileo L1 signals. And these included some configurable interference scenarios that we could play with, and it was very useful. The output from the simulator was recorded and processed offline, which allowed us to directly compare the commercial off-the-shelf benchmark receiver's performance with that of the RIM-enabled version that we are proposing in this work. And as shown in the diagram here with the system setup, the setup included two receivers, one serving as a benchmark and the other running the snapshot RIM pipeline, basically in order to do the benchmark analysis. And this was along with a signal recorder and converter for data capture. So we had a lot of options with this setup. And finally, I would like to mention that in order to ensure consistency, we decided to use interferences that were equivalent to the ones tested in the first experiment. Here we have the results with this experiment. Here, each plot compares three receivers. As I mentioned, the baseline snapshot receiver without mitigation in red color, the same receiver with RIM applied in green, so our proposed approach, and a professional commercial off-the-shelf benchmark receiver in blue. And as we can see across all three interference types, the continuous wave chirp and the pulse chirp, the snapshot RIM consistently and successfully outperformed the commercial off-the-shelf benchmark receiver. We particularly obtained gains of up to 20 to 30 dBs in average carrier to noise ratio. And we can also see that the snapshot receiver with RIM maintained satellite detection even at very high interference to signal ratios, like ratios that we can consider very, very high. And yeah, I would like to highlight that this shows that RIM enables robust detection and tracking under strong jamming conditions, even compared to this commercial receiver. So finally, to wrap up, this work was motivated by the growing trend of cloud-based GNSS processing and snapshot architectures, which are becoming, as I mentioned, increasingly relevant for low-power, scalable, and server-based positioning systems. In particular, we focused on providing robustness to the snapshot architectures through the robust interference mitigation framework, which is a pre-correlation method compatible with single antenna setups and that does not rely on prior knowledge of the jamming waveform. Since snapshot architectures often operate with low-bit quantization to enable these low-cost transmissions, we analyzed how the limited signal resolution affected the performance of the characterization of the full jamming signal and also of the snapshot RIM framework. And overall, the findings show that RIM achieves gains proportional to the signal resolution as expected, and that it remains computationally efficient, and that it outperforms the commercial of the shelf receiver that we benchmarked against. I would like to close saying that the results in this paper, I'm thinking of this paper as a way to highlight a path toward efficient and cloud-compatible interference mitigation in GNSS receivers. And I hope we can pave the way for next generation GNSS systems and make them robust and also scalable. Thank you very much for your attention and for staying until the end. I guess if you are interested in learning more about our work, please check out our paper and also feel free to contact me via email because I would be very happy to discuss further if anyone is interested.
Thank you, Elena, for this great presentation. We are now going to switch into Q&A, so we will now accept questions from the audience. And as a reminder, you can submit questions using the Q&A button in your viewer. So we can go ahead and get started with some questions.
So I see an anonymous attendee asks, in the introduction, you quickly mentioned the waveforms causing interference from the distance measurement equipment and tactical air navigation systems. Could you elaborate on these waveforms and on how you tackled them in the analysis? So this is actually a question that one of the reviewers asked us about. So basically, the DME and TACAN systems are both calculating the range between the range to an aircraft. So they're kind of similar to radar. They have a pulsed in time behavior. In the case of TEDCAN, I think it also has some azimuth estimation, and I think it's a military version of DME. But I consider that we covered this in the paper as well because we were assessing the impact of interferences that were also sparse in the time domain with the third jammer that is pulsed in time. So Ray Bagel asks if we have any plans to integrate and test with non-cloud connected receivers slash processors. Not that I know of. So yeah, my question would be no, not that I know of, but interesting. As I said, feel free to send me an email and we can discuss. Is there a possibility, Bruno Chiamolesir, sorry for my pronunciation, asks if there is any possibility of having RIM in smartphones and low-cost GNSS receivers. Yeah, I'd say this is the main goal of this work. We wanted to elevate most of the GNSS baseband processing to the cloud, which would leverage it would lower the computation that would need to be done at the smartphone level, like on the actual receiver that you have. So yeah, definitely, I think this work goes on the line of what you are proposing. Also, Bruno asks whether there is any relation between jamming and mask angle variation. So I guess, yeah, I don't know if you're asking whether if we change the mask angle in the receiver, we will be able to filter jammers. If you're asking this, my answer is that definitely yes, but yeah, this would be more at the front end side. So if that happened, we wouldn't observe the jammer at the IQ sample level that we have here. So it would be already clean. You you can kind of do something similar with the CRPA methods that I was introducing before. Like I would say the effect would be kind of similar, like when you do a null at the direction where you get the jammer. But then if you do that, you don't have the jammer at the IQ samples. But as I mentioned, you require multiple antenna elements. And also they are more expensive. That's why we propose RIM, which works with single antenna. Yeah, also Bruno asks on the application of different antennas with RIM and how would the results change, and whether the antenna power gain matters during the jamming times. So regarding the second part of the antenna power gain having an effect, definitely. But as I said before, I think this is also more on the front end side. So you can work on like retrieving the samples better by adjusting your ATC. But yeah, we haven't really explored RIM with multiple antennas. As I said, the motivation is to do it with single antenna so that it's cheaper. But I would be open to study whether the RIM applied to a beamformer would provide a benefit. It would be interesting. However, I think they might be complementary methods, but they are both mitigating the interference on their own, at least when they are sparse in frequency. So Austin Albright asks, what is high resolution quantization to us? In our case, we were referring to high resolution to the 8-bit case. But as you could see, I passed it super fast because I was a bit short in time. But here in the comparative analysis between RIM and the notch filter, we also tested up to 16 bits. I think you can consider 8 is high resolution already for GNSS, considering that you can even get position for even 1 bit in some conditions. Were you able to assess the impact of RIM on delay and Doppler estimates? This is a question by Julien Lesouple. So as I mentioned before, what RIM is doing is equivalent to applying an M estimator on the delay on Doppler estimates. And however, yes, it is true that the results that we showed didn't really they didn't show the final outcome of acquisition. But yeah, yeah, no, we didn't assess it in this work. But as I mentioned, you can check this paper here, which it is a very interesting paper. Actually, equations 13 to 17, I was checking recently, from this myriad nonlinearity for GNSS robust signal processing by Daniele Borio. Here Daniele explained how this M estimator on the delay and Doppler estimates is equivalent to what we do with RIM. How do you... Yeah, so an anonymous attendee asks, how do you expect the performance in case of more than one jammer present? When there is no regular period or structure over time in RFI, at least during a snapshot. So, although we haven't evaluated this experimentally, the key of the RIM framework is that you don't really need to have this previous knowledge about the interference waveform, as I've been repeating multiple times during the presentation. But also, this means that if you have multiple tones in frequency being affected, you will be able to mitigate them being this from one chirp or multiple of them. Like, my take on my guess is that we would definitely be able to mitigate multiple jammers, as long as they could be expressed having this sparse behavior in the transform domain. And I'm talking all the time about frequency because most jammer signals in GNSS are sparse in frequency because they're basically this continuous wave jammer, the chirps, and also some modalities of it. But in the end, it all resorts to the same. So my answer is that probably yes, we would be able to. Yeah. So another anonymous attendee asks something that one reviewer also asked. They say, since the receiver is being executed in the cloud, what impact could have increasing the sampling frequency in terms of computational complexity? It is feasible to obtain real-time positioning with moderate hardware. So, okay, I have an answer prepared with regards to how increasing the sampling frequency can impact ring performance. But regarding what you're asking, which I think is in the part of, like, if you increase sampling frequency, you're gonna have more cost in the hardware. I am not aware of whether that would be okay. I guess it depends on the application and on the power that you're okay with spending on this. But definitely increasing the sampling frequency is gonna increase the complexity. But at least I can really tell you also with these results that the percentage of outliers detected by RIM, statistically detected by RIM, is not going to be damaged if you increase the sampling frequency, precisely due to what I was explaining before here in this intuition behind the behavior of the chirp interference in the frequency domain. The continuous time Fourier transform always shows these equally spaced impulses, spaced inversely proportional to the chirp period. So if you indeed increase the sampling frequency, both if you keep the bandwidth of the receiver or if you increase it, you are not going to have higher outlier percentages observed because you're going to be sampling more signal, more useful signal, but sorry, you're gonna be sampling more jammer, but also more useful signal. So this proportion is going to remain very similar. So I can tell you, as of RIM, the more sampling frequency, actually, it could be better because you will have a more accurate representation of the signal. And in terms of complexity, I don't really have an answer, but I guess it depends on the power that you are okay to spend. And regarding how long are the IQ snapshots that you're using? So this is asked by Gary McGraw. Um, yeah, so as I mentioned, we were using 4.5 megahertz of sampling frequency and 1 millisecond of mini snapshot. So this is 4,500 samples. And then you can do this 100 times if you have a 100 millisecond snapshot. But of course, like doing the little FFTs leverages the expression of the computational complexity for the FFT tells you that if you do these little FFTs instead of a big FFT, you have a lower complexity. So that's not a concern. I hope I answered the questions properly. I don't see any other questions.
I think that's all for questions today. We want to thank everyone for joining us for today's webinar, and special thank you to Elena for your time and presentation. We want to remind everyone that a recording of the webinar will be posted to our website, YouTube, and social media by this Friday, the 24th. Also, if you joined today and you are not already an ION member, we encourage you to consider joining as a member to support our initiatives in advancing the art and science of PNT and to continue hosting webinars. Thanks again, and we look forward to having you join us at our next webinar taking place in December, and more details on that webinar can be found at ion.org.
Thank you.
Thanks, Elena.